Hello everyone. This week we will be talking about chapter 7.1, 7.2, and 7.3. These three are very short lessons, that's why I combine them together. Okay, so let's get started. 7.1 is inductive reasoning. What is inductive reasoning? What's the definition? The definition for inductive reasoning is that it's drawing a general conclusion from repeated observation of specific examples. Drawing a general conclusion. This is also called making a conjecture. From repeated observations. So we talked about making a conjecture. What is a conjecture? In math, a conjecture is a testable hypothesis based on the available evidence, which is not yet proven. And a conjecture may or may not be true. Okay, so conjecture is testable hypothesis based on available evidence not yet proven. These may or may not be true. So this is basically a educated guess. Now, let's look at a few examples of inductive reasoning. The most familiar one for you will be the Fibonacci number, right? So example 1, 1, 1, 2, 3, 5, 8. What is the next term? So you can tell from the two terms, if you add those two, you get the third term. If you add the next two, you'll be able to get the next term. So we know that if you add the previous two, you'll be able to get the next term. Now we know the two in front of this blank is 5 and 8, so 5 plus 8 will be 13, and 13 plus 8 will be 21. So our conjecture is that if you add the previous two terms, you'll be able to get the third term. This is our conjecture. This is our hypothesis. Okay, let's try another one. If I have the first term is 1, the second term is 1 plus 3, third term is 1 plus 3 plus 5, and then 1 plus 3 plus 5 plus 7. I know that 1 is just 1, 1 plus 3 is 4, 1 plus 3 plus 5 is 9, and then this is 16. What pattern can you see? If the question asks you to find the next term, what do you think the next term will be? So the question is, what conjecture can you make? If you take a look at these numbers, you can tell that these numbers are all perfect squares. 1 is 1 times 1, 4 is 2 times 2, 9 is 3 times 3, 16 is 4 times 4. So what would the next term be? I'll guess that it's 5 times 5, according to the pattern that we see here. So the next term will be 25. You can test our conjecture, or you can test our hypothesis here by adding these together. So we know that 1 plus 3 plus 5 plus 7 is 16. 16 plus 9 is 25. So we know that if you're adding all the odd numbers, it will equal to the perfect square of the number of terms. So it's 5 times 5 here because we have 1, 2, 3, 4, 5 terms. So if next I have 6 consecutive odd numbers adding together, then my answer will be 6 times 6. Okay, let's try another one. One times 9 plus 2 is equal to 11. 12 times 9 plus 3 is equal to 111, and then times 9 plus 4, this is equal to, and so what is this equal to? So from the pattern here, we can see that the first term is 11. That is 2 ones. And the next one is 3 ones. And the one after is 4 ones. You can see that the 2 give you, if you're adding 2, it gives you 2 ones. If you're adding 3, it gives you 3 ones. If you're adding 4, it gives you 4 ones. Then if you're adding 5 in this order, what would it give you? It give you, my guess is 5 ones. You guys can test this using your calculator to see whether our hypothesis is true or not. Okay, let's do one more. Example 4. If pattern is 20, 25, 31, 38, 46, then what are my next two terms? So from 20 to 25, we can see it's adding 5. From 25 to 31, it's adding 6. 31 to 38, it's adding 7. 38 to 46, it's adding 8. Then 46 to the next term, it will be adding 9. And then adding 10. So 46 plus 9, what does that equal to? It will be 55. 55 plus 10, it will be 65. So inductive reasoning is basically finding a pattern and predicting the next few terms. 7.1 asks you to find the next term or the next two terms, but 7.2 asks you to find the nth term. To do questions in 7.2, we'll need to find a general equation for the pattern. So we need to determine a relationship between the figure number and the value of that figure. So let me give you guys an example. If you look at this example, this is figure 1, this is figure 2, this is figure 3. Just like chapter 4, when you guys are working with linear relations, the easiest way to do these type of question is to make a table of values. So the right is the value, the left is the figure number. So for the first figure, how many triangles are there? The value of triangle is 1. We have one triangle. For the second figure, figure 2, how many triangles are there? There are 4. And if you're looking at the third figure, there are 9 triangles. If you keep going, if you do figure 4, then you'll see that there are 16 triangles. You can keep drawing more figures to see what the pattern is, but the question is, if you have the nth figure, figure number n, then how many triangles are there? So we need to analyze the pattern here by looking at the relationship between the values and the figure number. So here you guys can tell that 1, 4, 9 are perfect squares. 1 is 1 times 1, 4 is 2 times 2, 9 is 3 times 3. Where do we get the 1, 2, and 3 from? You can see that 1 is this figure number 1 times itself. 4 is figure number times itself. 9 is the figure number times itself. So if we have the nth figure, then what is my pattern? It will be n times n. So we know for the nth figure, the value will be n square triangles. We'll have n square triangles. Okay, so the number of triangle is equal to n squared. So if the question asks you, how many triangles are there in the, let's say, 10th figure, in figure 10? In figure 10, you will have 10 square, that is 100 triangles. Now let's do another example. Predict the nth term for this pattern, 3, 7, 11, 15. So again, we're gonna make a table of values. The left will be the term number, and the right will be the value of the term. So for the first term, the value is 3. The second term, the value is 7. The third term, value is 11. And the fourth term, value is 15. So let's see what the relationship is here. We know that 7 is equal to 3 plus 4. 11 is equal to 7 plus 4. 15 is equal to 11 plus 4. And we also know that 7 is equal to 3 plus 4. So 11 will be 3 plus 4 plus 4. And 15 will be 3 plus 4 plus 4 plus 4. If we make it shorter, if we change adding to multiplying, then it's equal to 3 plus 4 times 3. And 11 is equal to 3 plus 4 times 2. 7 is equal to 3 plus 4 times 1 because there is only one 4. And the first term is equal to 3 plus 4 times 0, right? So if we have the nth term, then what is the value of the nth term? We know that it's always 3. It's always 3 in the beginning, and we're always adding 4 times something. Now, what is that something? Let's look at the something. Compare it to the number of terms. If the number we're multiplying is 0, our term number is 1. If our term number is 2, then the number we're multiplying is 1. If it's 3, then it's 2. If it's 4, then it's 3. What do you see there? The number we're multiplying is always 1 less than the term number. So if the term number is n, then what would be the number we're multiplying? It's always 1 less, so we need to minus 1 from n. So the value of this term will be 3 plus 4 times n minus 1. There are a lot of examples in your workbook that you can refer to, but it takes time and practice to find the patterns and find the equations. So please try some examples in your workbook for practice. Next, we're going to talk about counterexamples. A counterexample is an example that is inconsistent with a general statement and may be used in argument against it. So counterexample proves the statement false. Okay, let's do 2 examples together. First one, every prime number is odd. Is it true or false? If it's false, you need to find a counterexample. So obviously this is false. What counterexample can you find? We know that 2 is a prime number, but is 2 odd? No, 2 is even. So we've proved that this statement is false by giving 2 as a counterexample. Okay, question 2. For any real number x, x squared is greater to x. Is it true or false? Well, it's false. I can find a few counterexamples actually, but you just need one counterexample to prove the statement false. Okay, so one of the counterexample you can find is 0. If x is equal to 0, then 0 squared is equal to 0, not greater than 0. 0 squared is always 0. It's not greater than 0. Okay, I can find another one, 1 squared. 1 squared is equal to 1, not greater to 1. What about 0.5 squared? 0.5 squared is equal to 0.25, which is less than 0.5. Right? This is 0.5 squared is not greater than 0.5. So these counterexamples proved the second statement false. 7.3 is deductive reasoning. It's a method of drawing conclusions from facts that are accepted as true. Let's look at a few examples together. So a general statement is all English teachers like to read. So this statement is accepted as a true statement. And the first argument is that Sam does not like to read. If Sam does not like to read, but all of the English teachers like to read, then what conclusion can you draw here? Then you know that Sam is not an English teacher. Okay, for the same statement, the second argument is that Lisa likes to read. What conclusion can we draw here? Do we say that Lisa is an English teacher? No, we can't draw that conclusion because the statement only says English teachers like to read. It doesn't say about any other people. right? Maybe some other people also like to read. Maybe lawyers like to read as well. Lisa likes to read doesn't necessarily mean that Lisa is an English teacher. Okay, so from this argument, we can't draw any conclusion. We, we don't know if Lisa is or is not an English teacher. So Lisa may or may not be an English teacher. One last example. Um, the general statement is that a person must be at least 12 years of age to have a fishing license. And we have four parts to it. The first one, Sally has a fishing license. What do you know about her then? If she has a fishing license, we know that she must be 12 years or older. So Sally is at least 12 years old. If she is less than 12 years old, then she will not be able to have a fishing license. Okay, next one. Laura is 15 years old. What do you know about her? She is 15 years old doesn't mean that she has a fishing license because she might not like to fish, so she doesn't get one. So from this argument, we can't draw anything. Nothing. We don't know anything about her. We just know that she's 15 years old. We don't know whether she has a fishing license or not. Bill went fishing. What do you know about him? He went fishing doesn't necessarily mean that he has a fishing license. No, right? He might just went fishing with his parents or with his older siblings or people like that. Right? So we can't draw any conclusion from here. Nothing. Last one. George is under 12 years old. Well, we know that if you want to get a fishing license, you must be at least 12 years old. So if he's under 12 years old, then that means he does not have a license. All right, you guys can try these questions for practice. I do really like this chapter. I think it's fun to work with.